We will be taking notes. Okay, so we've got to talk today about the nature of light. I'm glad you guys had a little bit of fun with those glasses. Okay, hopefully you saw the world in a little bit different color, right? Okay. In a different light. Ooh, there we go. I like that. Okay. All right. So one of the goals of this unit is that we're going to talk about how electrons behave inside of atoms, specifically inside of the hydrogen atom. Okay. Before we can talk about how electrons behave inside of the hydrogen atom, we need to understand the nature of light in general. Okay. The word light, the way we use it in our everyday lexicon, is for visible stuff, right? If I say light, you think, hey, we're going to talk about Roy G. Biv, that colorful dude. You guys know about Roy G. Biv, right?
Of course.
Roy G. Biv is the easy way to memorize the colors of the rainbow in the correct order. My wife hates that I know Roy G. Biv because we have colorful plates, and I have to stack them in the right order when I, unload the dishwasher. She complains because I unload the dishwasher.
That's a good system.
Okay. All right. I should take a picture and show you guys. But at any rate, here's the idea, is that light, when we use that term in science, it doesn't mean just the colors. It also means the other parts of the electromagnetic spectrum. Light is only the visible part. Okay. This list is in order, and you want to write it down in this order because the left side of this list contains the highest energy of the electromagnetic spectrum, so the highest energy of light. Gamma waves are the highest energy. X-rays are the next lowest. UV is the next lowest, followed by the visible light spectrum. Infrared, micro, and radio. Radio waves are the lowest. I can't spell lowest. Energy of our light waves. Okay, which is pretty good because right now you're getting hit with radio waves, right? Have you ever thought about that? Taking a moment. Can you tune a radio station inside the school? Yeah, right. How many stations could you tune in? How many stations are in the Chicagoland area here? Right? There's quite a few. There's a couple dozen. How many radio waves are hitting your body right now?
Maybe that's why I have a headache.
Okay, there's a couple dozen radio waves hitting you right now. You don't have any equipment in your body to detect that, though. Your eyes do a great job of seeing the visible spectrum, but they're not set up well to see anything else.
What do these glasses do?
What do these glasses do? Those glasses are prisms. Okay, so they're called diffraction grating that's in them. And basically all they do is they take the colorful spectrum of light and they separate out all of the colors that are in it. Okay. I'll show you guys something cool if we get a chance in the back of the room. I know that you guys can see with those things all of the colors. I can show you only some of the colors with something else. Light can behave as a particle or as a wave. Okay. All right. You probably want to draw yourself a nice sine wave here so you can write down some of the properties of a wave. Okay. One of those things is the wavelength, the length of a wave. I think in the video yesterday they pointed out that the wavelength is usually measured from the crest of one wave to the crest of another wave. Okay. Amplitude is another term. Amplitude talks about the intensity of the wave, and that is the height from the center, from the midline, to the crest. And you can see that both those pictures are kind of, well, they're repetitious. Okay. I think the most important thing on here is wavelength. You guys want to write down this Greek symbol, lambda.
Lambda.
Okay, going to college, you need some knowledge. This is good if you're joining a Greek order. So you need to know your Greek letters. There's lambda. Okay, lambda is the same thing as wavelength. It's just what we use to abbreviate it in our equations.
That's part of the B and the B.
All right. So the other property that we're going to be extremely interested in knowing is frequency. Frequency is abbreviated with the Greek symbol nu, N-U. A little bit easier to say. Notice, guys, it looks like a cursive V when you write it. Okay, it's a V with a tail. It's the number of and frequency is the number of waves that pass through a particular point in 1 second. We use units for frequency of hertz or in times per second. Hertz and times per second are the same thing. All right, this is a little bit repetitious, so you might want to go back up where you wrote the electromagnetic spectrum in order. There are 7 kinds of waves. Radio waves has the least energy, remember? And gamma rays had the most energy. Something else to write down about it is that gamma has the highest frequency. Okay, so most energy and highest frequency are the same thing. So just for the sake of argument here, let's say that the frequency of a gamma ray is 10 quadrillion hertz.
That makes sense though, because frequency, they come together.
How many times do you get hit by a gamma ray that's 10 quadrillion hertz?
10 times per
Right.
second.
10 quadrillion times in a second. Will that have more energy than a radio wave that's like 1 hertz?
Is that what you
Yes.
Yeah. Okay.
So frequency is the same as energy?
So
You said?
frequency and energy are related,
Oh,
proportionally related. Okay, your amount of frequency and your amount of energy are proportionally related. The difference here is this: the wavelength of a gamma wave has to be really, really short in order for it to have a high frequency. So check this out. If I was to draw a oh, that's not a good gamma wave. If I was to draw a good gamma wave, it's going to be like this. Okay. Notice there's no wavelength here. There will be math. Okay. Radio waves, on the other hand, have the lowest energy, which means they're the lowest frequency. They don't hit you as often. And they're going to have the longest wavelength. So a radio wave is going to be something more like this, as far as a conceptual model is concerned.
Lowest energy, lowest frequency.
Lowest energy, lowest frequency. And longest wavelength.
So the wavelength and the time energy or the frequency are inverse.
Frequency and wavelength are inverses. This is a good thing to know. The other thing that's on this slide that you guys need to memorize is the wavelengths of visible light. We want you guys to know that we can see things from 400 to 700 nanometers. Guys, is that visible spectrum of light in the visible spectrum on this particular thing is drawn way too wide. It's actually only supposed to be as wide as one of these black lines, but then you wouldn't notice it, right? So they made it that wide. So the portion of the spectrum that we can see is tiny, minute. All right. Ooh, speaking of things that are going to make you feel tiny, you know how fast light moves?
6.02 times 10 to the 25th.
Nah, it's not a mole. All right. Light moves at 3 times 10 to the 8th meters per second. Okay.
That's really fast.
That's to say a 3 with 8 zeros after it.
Arches can move faster.
I don't even think Pikachu can move this fast. All right.
Yes, he can.
300 million meters in 1 second. And yet the light from the sun takes 8 minutes to get to Earth. Okay, so it's really, really fast. I've included a second set of units there, 3 times 10 to the 17th nanometers per second, because usually for our purposes, we're dealing with visible light. Visible light is measured in nanometers, so this is going to be a more useful constant for the speed of light for us. Okay. And to try and tie this all together, the three facts that were on the past couple of slides, it turns out that the speed of light is a constant. All electromagnetic waves move at that speed, whether you're a gamma wave or a radio wave. All of the waves move at that same 3 × 10 to the 17th nanometers in 1 second. But what's interesting is that the frequency times the wavelength always equals the 3 × 10 to the 17th nanometers per second. So, for example, we might be thrown a problem like, hey, red light has a wavelength of 691 nanometers. What's its frequency?
All right. So,
Okay.
1 minute.
691 nanometers equals wavelength.
I know what it is.
Okay, and nanometers is a measure of wavelength, so I'm actually going to rearrange my equation so that wavelength is on that side so that frequency can be found by taking C over wavelength. I am algebraically manipulating that equation to solve for nu, for frequency. Okay, so frequency is C over wavelength. C is 3.00 times 10 to the 17th nanometers per second. Wavelength was given as 691 nanometers. Can you guys see why I chose that particular version of C?
Yes, because it's
It's already
already in nanometers.
in nanometers.
Oh, no.
Nanometers and nanometers happen to cancel when we do this. We're left with per second. If your brain is starting to hurt, you know what units we're going to get here. What units will we get? Oh man, you guys missed the pun.
That really hurts.
Yeah, it really does hurt that you guys missed that pun because that was so obvious, I think. All right, the units are hertz. Thank you, Aubrey. All right, so then we're going to take 3 × 10 to the 17th. We're going to divide it by 691. Aubrey loves sig figs. She knows we need how many sig figs?
I'm not even
3.
3. Good. All right, so calculator says 4.34 times 10 to the 14th.
Oh, I got 2, 3, what?
Okay, so go ahead and try this one out and see what you get. B, C over nu.
Oh wait, I did mu over C.
Wait, what?
Hang on, did I do that wrong?
No,
Yeah, I did it.
What's mu?
I did see it
It's a
from you.
Pokemon. Thank you, Brett.
Nu is the frequency. What's nu with you? All right, so 3.00 times 10 to the 17th nanometers per second should get divided by the frequency that they gave me, which was 6.00 times 10 to the 4th hertz. Now, when we took notes, we noticed that hertz and per second were the same thing. So hertz and per second cancel. The only thing we're left with is the nanometers. Our expert in the field, Aubrey, how many sig figs?
3.
Good. So when I write this down, I'm going to write 5.00 times 10 to the 12th nanometers. Okay, so guys, if we're also asked what region this falls in, we need to look back at this sheet and we need to look for where this falls.
Right in the radio.
10 to the 12th looks like it's about here for wavelength. So I'd say that it's some kind of radio wave.
You have to memorize
Okay.
this.
No, you don't have to memorize this. You just have to use it to look things up. So don't